my pleasure to be able to introduce Fengqi Yu. He's the Roxanne E. and Michael J. Zach Professor at Cornell University. Previously, he received his bachelor's degree from Tsinghua University and received his PhD from Carnegie Mellon University. He served on the faculty of Northwestern University from 2011 to 2016 and also worked at Argonne National Labs as an Argonne Scholar from 2009 to 2011. He's published over 100 peer-reviewed articles in leading journals and has an H-index of 40. Some of the awards that he's received are the Northwestern Argonne Early Career Investigator Award in 2013, the National Science Foundation Career Award in 2016, and numerous other awards. He's currently an associate editor of Computers and Chemical Engineering. He's a consulting editor for AICHE Journal and on the editorial board of several journals. His research focuses on the development of novel computational models, optimization algorithms, statistical machine learning methods, and systems analysis tools for process manufacturing, smart agriculture, energy systems, and sustainability. So with that, I'll go ahead and turn it over to Fengqi Yu for his presentation. Thanks and welcome, Fengqi.
All right, well, thank you very much, John. Thank you for the introduction and thank you for the opportunity to present here. Well, good morning, everyone. I see some of you are from the other side of the world, so probably good afternoon or good evening. So anyway, thank you for participating in this presentation. So we are a bit late, so let me try to just cut directly into what we are going to talk about today. Focus today is really talk about decision-making under uncertainty, but from the data lens. So many of you probably have already working on this area of optimization under uncertainty. And the classical approach that we are taking is kind of following a three-step approach. So the focus on optimization under uncertainty from the conventional approach is essentially dealing with mathematical programming models and algorithms with the input from some sort of uncertainty model, okay? And with the output, essentially, if you trust the optimization theory, we end up with optimal decisions. In this particular case, you can see the direction from optimization model and algorithms to the optimization outputs are essentially validated because the theory solve is guaranteed. On the other hand, the input of these optimization model and algorithms really come from some sort of uncertainty model. And this uncertainty model usually coming from fitting certain kind of data to a no probability distribution or to a no uncertainty set. Okay? And this is really a one-direction flow. So what does that mean is essentially when you try to pick up this uncertainty information, we assume it's correct, we assume it's accurate, we assume it's perfect. And then we try to leverage this information in our optimization, in our decision-making process to make a decision. So here is the issue. You can see from the graphic here, for example, when we have one-dimension uncertain parameter and we have some histograms, we could try to fit into some kind of probability distribution. And there are certainly certain fitting errors, okay? But in this entire process, in a conventional approach, there's no way for us to reduce the fitting error because it doesn't really go back. So what we say, this approach is somehow closing the loop on the later part. Okay, we close the loop between optimization input and output, but we did not really close the loop with the uncertainty information. And what we see in practice, in industrial practice and academic research, is essentially a lot of uncertainty information was generated from data. And this data will be historical data. It could be real-time sensor data from Internet of Things or from any type of physical systems, or it could be even forecasting data. And these data could usually be very complicated. They could have very high dimension. They could be correlated. They could be asymmetric. They could involve multiple modes and multiple classes. Okay. So with the very kind of messy data or complicated data, if you still use the conventional approach to fit this kind of uncertainty model, the fitting error could be sufficiently large in certain cases. And it really causes an issue because even you solve the problem to 0% global optimality gap, the optimal is only corresponding to the fitted uncertainty model, not corresponding to the true uncertainty information. So that's why we are trying to look into this problem from a data lens. You know, when you have data, pretty big data, but in some cases you get medium data, sometimes you get small data, but essentially you get some kind of uncertain data. Again, it could be historical data, real-time data, could be forecasting data. And we are trying to see how can we make a decision in an optimal way starting from the data. Okay? So there are two kind of major steps or two major issues involved. The first issue is, of course, we can think about data and how to extract this information from data. Actually, useful information, accurate information to build these machine learning models or leveraging these machine learning algorithms. In this particular case, we definitely want to have this cross-validation in the way the data could be corresponding to the uncertainty information, and the information would accurately and correctly capture all the information from data. And the next step is hopefully this machine learning model and algorithm will be seamlessly or organically integrated with mathematical programming, okay, so that you could have these bidirectional flows in both sides from the data to the decision. And this is the main idea about data-driven decision-making on the uncertainty. We try to have a holistic, systematical framework to capture everything between the data and the decision, okay? And this data-driven decision-making framework would involve some kind of data-driven components. Essentially, data-driven components will be capturing the data information we get, information from uncertain data, and there could be some kind of model-based components, essentially in these mathematical programming models and algorithms. And these two parts to be integrated together, it's a marriage or it's a perfect merge. And I would always like to argue that 1 plus 1 it could be greater than 2. And in this particular case, you will see later on, 1 plus 1 is greater than 10. Because the merge is not a simple integration. In the end, it could really lead to some new and fundamental developments in the modeling framework and in algorithms in both fields, the machine learning field and also the mathematical programming field. And again, this is the key idea of data-driven decision-making under uncertainty, and it's one of the emerging areas in the research. And the key focus is how can we combine these two sub-areas together, from machine learning to mathematical programming. So a little bit on history. The key idea here is to really let this data to speak in mathematical programming. So still it's looking into the problem from optimization perspectives. And the classical work, or the seminal work was done by Inye from Stanford about 7 years ago, and looking into this distribution robust optimization. Even now, distribution robust optimization is still a very active area in operation research, in control, in systems community broadly. Another piece of recent work was looking into this called data-driven chance-constraint stochastic program. So this really started another sub-direction in this area. But one of the key focus in the past few months or past few years is really looking into data-driven, static, and adaptive robust optimization. And the main interest about this data-driven robust optimization is because of the feature that could really nicely balance the solution quality and also the computational tractability. So the seminal work in this data-driven, robust optimization was given by Basimas and co-workers, a paper published early this year in mathematical programming, and what it is looking into this data-driven static robust optimization, and it became one of the first merge when machine learning meets robust optimization. So my group has been working on this topic as well, and we have been dealing with a few problems, essentially looking into data-driven robust optimization with kernel learning, and some will work on data-driven adaptive robust optimization, which we will introduce later on to show the advantages compared to the classical static robust optimization. And we also extended to the multistage ARO, as well as the very recent unified framework for the data-driven stochastic robust optimization. So most of this work was done by the PhD student Chao Ling and the postdoc Chao Shang. They are wonderful students that I have the pleasure of working with. So in this presentation, I will introduce the second piece of work, data-driven adaptive nested robust optimization in sufficient details. And if time permits, we could talk briefly about the data-driven stochastic robust optimization. And at the end of the presentation, I will also briefly introduce the other two pieces of work on data-driven robust optimization based on kernel learning and the one on multistage adaptive robust optimization. So for some of you that do not have sufficient background in robust optimization, let me try to review some basic concepts and major information in this field. So robust optimization is not new, has been around for almost more than 4 decades, I would say. So back in the 1970s, people are looking at things called static robust optimization. And this is the classical way of looking at robust optimization in a way, looking to this minimization of a certain derivative subject to the decision variable x, within the maximum variability of the uncertain parameter u, okay? And this is what we call a single stage or static robust optimization. So what you can see here is a minimax problem. So essentially it's the multi-level optimization problem or bi-level optimization problem. And there are two major components in this particular problem. The first one is the decision. And decision is given by decision space x. And here in this particular case, for the static robust optimization, it allows and assumes all the decisions are met here and now. Okay, so it doesn't really have too much flexibility because assume all the decisions must be met before you see the uncertainties realized. The next component is about uncertainty, and the way robust optimization describes uncertainties is using something called uncertainty set. So essentially it's a model, mathematical model to describe uncertainty information. And again, in a classical static robust optimization, this uncertainty set is usually constructed based on some kind of a priori information. and usually they use some kind of relatively simple information about uncertainty. So with this approach, of course, there are a lot of criticisms, and the main criticism is people feel that this approach tends to be overly conservative, okay? And because there's no flexibility on decision, and the uncertainty set does not really capture what's going on, tends to be too more conservative. So we'll get into these two parts later on, but let's say first, looking at the decision. So what can people do to improve decisions to make it better? And in the past few years, or past 2 decades, an emerging field is looking into adaptive robust optimization, or adjustable robust optimization. So essentially the idea is instead of looking into only one-stage decision for here and now we were looking into two-stage or multiple-stage decisions. For example, you could look into the two-stage ARO. In this case, you could have decisions that are made here and now, decision variables X, and then you can have some decisions made in a wait and see mode, more like recall decisions, like decision space Y, okay? So wait and see decisions will make after this uncertainty is revealed, and they can really present this kind of sequential decision-making process. So this really introduces more flexibility to adjust the conservative issues in certain way. And the recall decisions are really helpful because they can also adjust a lot of feasibility issues that we see in the conventional static robust optimization. So the other piece of improvement is not only in decision space, but more in the uncertainty set. And in fact, you could argue in some way, uncertainty set is really the heart of robust optimization. It's the intellectual core. Everything about robust optimization is really built based on the uncertainty set. How you represent uncertainty and how you capture uncertainty. And as I mentioned earlier, back in the 1970s, everything tends to be very conservative at the time. So people use a box uncertainty set, and this is something easy. Okay, when you have uncertain parameters, you try to get upper and lower bounds, UL and URU, okay, and then you just say, okay, we want to have a box uncertainty set, make these uncertain parameters between upper and lower bounds. So this kind of presentation is certainly very easy, very simple, and very treatable, easy to solve. But you can see in the later on, in this uncertainty set case, the major weakness or major drawback is that the solution tends to be very conservative because we have to cover a large range of uncertainty space. So things get improved in the 1990s, people looking into some kind of nonlinear uncertainty set. In this case, it's elliptical uncertainty set. Okay, we can use some kind of quadratic function or nonlinear function to capture uncertainty information. So this tends to be better, a little bit better to control the conservativeness. But still, the weakness is on one hand, you have to introduce nonlinear functions to the model. They could really contribute to the computational challenge. And the other issue is that this kind of uncertainty is still symmetric and sometimes cannot really capture the correlated uncertainty information. So going to the year 2000, not too far ago, about 14 years ago, there's a very famous paper by Basimas and Sin looking at the budget, or sometimes people call gamma uncertainty set. And the idea is introducing these budget parameters to control the conservativeness. So now what you can see is from the previous case, the box set is essentially the entire range from upper and lower bounds. Ellipse is a little bit better, and now with the gamma set, you do see a nice diamond shape in this particular case. Of course, we need to choose the budget parameter carefully and correctly. But still, the weakness of this kind of gamma set is really kind of most suitable for independent uncertainty, and still the uncertainty set is somehow symmetric in certain way, do not have enough flexibility. So recently, the focus is really looking to something called general structure polyhedral uncertainty set. Okay, so hopefully you could have a very flexible structure to describe this uncertainty in a polyhedral way, multiple facets. And this sounds interesting and sounds promising, but always there's a challenge. How can we derive the right or optimal polyhedral coefficients? For some of you that are familiar with integer programming, you probably understand the complexity of deriving a convex hull given a set of integer variables. Okay, so even now you are giving a few points. Let's say in two-dimension case, you can easily draw the convex hull, the tightest polyhedral set. In three-dimension, maybe you could do that. Okay, but if you go to four-dimension, five-dimension, or even any random higher dimension cases, how can you come up with the tightest relaxation? Or how can you come up with a nice polyhedral uncertainty set to cover all or most of this data? And it's really challenging. And in fact, if we could really solve this problem, we could solve all the integer problem problems by just solving this LP, linear program relaxation of a convex hull. Then in that case, P will be equivalent to NP because linear program could be solved in polynomial time. But integer program problems are essentially NP hull problems. So that's the challenge. So going back to what we talk about this uncertainty set, and there are really a few research questions that we need to address in this work. Okay, so just by reviewing what we see in the previous pages, the box set, the ellipse set, and also the polyhedral set or even the budget set, if you wish. All these classical uncertainty sets are based on some kind of fixed geometric shape. So what that means is we come up with the uncertainty set by models, by equations, and we have a shape. And then we try to use this shape to describe uncertainty. Hopefully they fit. If they don't fit, we just try to adjust the parameters. The other issue is we try to have these sets as convex sets, okay? And of course, we want to make it convex so that it could be easy to solve. But, convex may not be the best in some cases. The last piece issue is that we always use one set fits all. So what that means is in any problem, we typically assume, at least for all existing literature from except our papers, people tend to use one uncertainty set to describe uncertainty, and they assume one set really fits all. So these are research questions we try to answer. How can we derive a model, or how can we derive the uncertainty set, uncertainty model, based on a given set of data? I mean, this is what we talk about, the data-driven approach, right? So if you have some sort of data given on the right-hand side here, how can we derive a polyhedral uncertainty set, let's say, in this case? Of course, convex will be difficult, but there are some machine learning tools and machine learning methods that could help us to derive this polyhedral uncertainty set, to determine optimal or relatively good coefficients of polyhedral uncertainty sets, okay? The next question is, why do we need to always use a convex set for uncertainty? I mean, of course, convex set is easy to solve, but just looking at this example here, okay, we have a polyhedral set, which is convex, but maybe a non-convex set like this, okay? Maybe a non-convex set like this would be better, because they could really capture what's going on about the data, capturing the data structure, capturing the data complexity. So maybe you could think about something like piecewise linear uncertainty set. Even if it's non-convex, it could be better. And the third research question is really, why we need to use one set? Can we use many sets, many small pieces of basic sets to cover all these areas, to capture uncertainty? And in some cases, of course, this could be non-convex, but that's okay, because once you have a large number of small pieces, basic sets, basic convex sets, okay, something we could easily solve, it's not just using the puzzles to cover this data. And eventually, as long as we cover all this uncertainty information, we could capture them in a very compact way, we are good to go. Okay, so these are kind of fundamental research questions we try to answer in this work and in the research direction. So one comment I want to make here is really, if you try to see the merge or the meeting between machine learning and robust optimization, they not only lead to a new data-driven methods, okay, but also they really contribute to the new mathematical programming paradigms. They contribute to the fundamental tools and methods you see in mathematical programming and fundamental tools and methods you see in machine learning. And many of these things like, non-convex sets, multiple basic sets, even these piecewise linear sets are really previously intractable if you really constrain by classical uncertainty models or classical uncertainty sets. All right. So let me give you a very quick example before I introduce you to technical details. So let's say we just get some uncertainty data here with two uncertain parameters, U1 and U2. All right. So U1 and U2 would have some kind of data we collected from history data, real-time data, and so on. So you get to see most data in the central part of the area, but there are some kind of green areas, green dots on both sides. These are some kind of, say, outliers, if you wish. So with the box uncertainty set, of course, as I argued earlier, they really take upper and lower bounds. So it turns out to be highly conservative in the way they try to capture the entire region, in a very comprehensive way. But somehow unnecessary, because why you need to worry about this blank space? There's no uncertainty data we're going to involve in those areas. But if you use this uncertainty set, you can really kind of try to solve the problem to hedge against all the uncertainty in the entire box area. And it's not good. So with the budget set, of course, one could adjust the budget parameters, and in some way, you could come up with something that is tighter than the previous case, and also screen out or filter out all these outliers, and just to focus on the most important information. But still, you get to see some blank areas all around, right? So that's what you can see in the data-driven uncertainty set, and that's something I'm going to introduce in the next few minutes, okay? The idea is to use some kind of basic polyhedral set, okay? A few basic polyhedral sets to capture the data structure and capture the data complexity. And it becomes a very compact representation about what's going on with uncertainty data. So what you can see here is really comparing this figure with this guy. We have a lot better, right? We cover what we need to cover, and we don't cover those areas that we should not cover, all right? And sample compared with box, of course, is even better. So taking a step further, you can always adjust the parameters, just which is you may know about in budget uncertainty set. You can always adjust the budget parameters, changing from 1, which is a blue area, to 0.5, which is a green area, or to 1.5, which is the yellow one. okay, and with different shapes. And you could do the same for the data-driven set, just adjusting these parameters and changing this data coverage area from 15% to 93% to 98%, okay? So that's something, a simple example to illustrate the power and to illustrate the applicability of the data-driven approach. And again, the comment here is the key idea here is using a few disjunctive sets for uncertainty modeling. And this is really some kind of out-of-the-box idea because essentially if you just try to follow the classical one-set-fits-all approach or the classical, fixed shape uncertainty set approach, you will never reach this point, okay? So somehow this is a data-driven scientific discovery in certain way, with the data approach, with the data-driven approach, we come up with new insights. And in turn, we contribute to the fundamental theory in robust optimization, specifically, or to mathematical programming broadly. And also, I would argue in this particular case, even you have some kind of set like this, it's not a straightforward approach. In the end, you still need to develop new modeling frameworks and new algorithms to adjust this kind of data uncertainty set, because they are not straightforward, they cannot fit directly into the existing modeling framework. The current setup of robust optimization, the current setup of mathematical programming cannot deal with this kind of data-driven framework directly. And that's the full research challenge. So a little bit technical details, how we construct this data-driven uncertainty set. So essentially, we try to build a bridge, okay, a bridge between the data and the information, okay. When we talk about uncertainty set, which is very important in the robust optimization, we begin with data, okay. In this particular case, we use the directional process mixture model, which is one of the nonparametric Bayesian model, okay. And then we calculate the predicted posterior, and eventually reach out to uncertainty set. So for those of you that are familiar with machine learning, you probably know this is called graphical model of the DP mixture model. So essentially for the directional process mixture model, it has a very nice property that the model could adjust its complexity based on the complexity of the data or based on the structure of the data. And the main idea of adjusting complexity is through this kind of stick breaking approach, essentially try to determine the number of components they need based on a certain data. And that's why in the end you can see in this graphical model, we do have an n dimension here, okay? So this sounds a little bit abstract. So let me give you a very specific example here about the directional process mixture model. Let's say we have a single dimension, just one single uncertain parameter with some histogram, okay, given in the center of this slide. And we can see, okay, this is definitely not a normal distribution, right? It's not a triangular distribution, it's not a uniform distribution, not something we know typically. But it could be a mixture of some distributions. So one way people could do is something looking into this called parametric mixture model. For example, a Gaussian mixture model. Essentially consider this distribution as a mixture of multiple Gaussian distributions, okay? And for this parametric model, what you need to do is you need to specify the number of parameters for each particular distribution, and you have to specify these numbers before you solve the problem, okay? This number has to be specified a priori. And assuming you don't know there are three components, you say, okay, we just use two Gaussian distributions to approximate it, given that here, two Gaussian distributions, now you will need 6 parameters in total, because you need a mean, you need a standard deviation, and you need a weight of each distribution. So 3 parameters for each, and 6 parameters for both. And still, if you do this with two components of Gaussian mixture distribution, they won't fit very well, okay? Because essentially you can see this is a 3-mode case. All right, and again, this is a one-dimension problem. I mean, we can visualize it very clearly. But human has a difficulty looking into the data in a higher dimension. Essentially, if you have the data with 4 dimension, 5 dimension, it's just no way to visualize in a very clear way. Okay, so we have to rely on some systematical approach to handle it. And this is how this nonparametric model really get into the place, because the directional process mixture model has infinite number of dimensions, and it could automatically infer a number of components based on data structure and data complexity. So if you apply DP to this particular data set with the stick breaking, they could automatically infer the number of components will be 3, and then calculate corresponding mean and standard deviation of each component. And this will turn out to be a nice fitting, a nice capturing of all the information you need we get from the data. Okay. So with the DP mixture model, what we did follow is the variational inference to calculate necessary parameters we will need for inference results. And in this particular case, we try to minimize this variational distribution, to minimize the evidence lower bound. And essentially, it's an optimization problem that we try to see how this variation free energy reduces until it really converges to the minimum. And with the inference results, we could further translate these parameters into the uncertainty set. And this translation is based on the predictive posterior, which I won't get into too much details. And the key idea is here is more much a mixture of a student t-distribution. So with this, we could have primitive uncertainty. We also have the weights in uncertainty sets. And again, the key idea here, key point I want to stress is we have a number of components from this DP mixture model. And each component would correspond to one basic uncertainty set. And that's how you can see in the earlier example, we end up with multiple basic uncertainty sets to cover the entire uncertainty space, the necessary uncertainty space. Okay? And that's how this number of components come out. And this number of components, again, will infer automatically and systematically from the machine learning algorithm. So with this, we can move forward, okay, with the uncertainty set definition given in the form here. And again, the key idea here is the union of multiple basic sets. Instead of using one set fits all, that what people typically do in the past, we try to use multiple basic sets for high fidelity description of uncertainties. And it's probably the first time I've seen all the existing literature on robust optimization that use these multiple basic sets to cover the uncertainty space, the necessary uncertainty space. Then for each specific pieces, for each specific basic uncertainty set, essentially we're looking into two things. One is the L1 norm. This is essentially the budget uncertainty set. And the other one is L infinite norm, essentially the box uncertainty set. Okay. So what does that mean? So we are looking to the intersections between the L1 norm ball and L infinite norm ball. So if, let's say, in the left-hand side over here, if the budget set is less than the box set, then the intersection will be the inner area here. Okay. If the budget set and the box set has some kind of overlap, then we end up with some kind of diamond shape, still a polyhedron set. And you argue this seems to be symmetric, but that's okay because eventually we have multiple of these at different positions, so they can really cover the entire space in a necessary way. So when we really go to these multiple basic sets, it doesn't really matter what the small pieces will be, how the small pieces look like, because eventually you could have many small pieces to cover any shape you like. So it's a highly flexible structure. So based on uncertainty set, we could definitely take a step further, looking into this adaptive robust optimization framework, and that's what we call about data-driven adaptive nested robust optimization. So here is how it looks like in a general form. So instead of looking into the classical min-max minute problem, okay, classical adaptive robust optimization is the three-level optimization problem, min, max, minute. And here we have one more maximization, okay, so it becomes min, max, minute problem. So the main feature of this model, of course, you probably could realize that is that the size of this problem would depending on the data, really depending on the data structure, depending on the data complexity. Why? Because we have the number of components, okay. The number of components will be inferred from a data structure automatically and systematically. And the number of components will be further translated into the uncertainty set here and eventually get into the optimization problem. Okay, that's why we also get actual maximization here over all the components. And the uncertainty set is not a single set, but a multiple basic sets. And then we're taking the union of all these sets. Okay. So with this multi-level structure, min, max, minute problem, we could well capture all these data-driven uncertainty set in the robust optimization framework. And so then there are some advantages. Key advantages, of course, the data-driven uncertainty set is adaptive to the uncertainty information. And so then it could be less conservative. It's less conservative because uncertainty set is pretty good, but also because we're looking into adaptive robust optimization. We are not doing the single stage static robust optimization, but looking into adaptive robust optimization, which is two-stage or it could be multiple-stage. And the key point here is we really capture the nature of uncertainties data, capturing the structure and the complexity of uncertainty data. But you get what you pay, always, okay? The question is how can we solve this problem? Because it's so powerful, it's so nice, but you end up with a multi-level optimization problem. And there's not really any off-the-shelf optimization solver that could help you to solve this kind of problem directly. But of course, there are some approximations, as always. So you may have heard about something called decision rules. In fact, this concept was borrowed from the control community. Okay, one classical and well-known decision rule is the linear decision rule or affine decision rules. And this has been popular nowadays by many applications and publications. The affine decision rule, essentially what they assume is that they see all the wait and see decisions Y or second stage decision Y must be expressed as a linear function of uncertainty or a affine function of uncertainty. Okay, so this is really a kind of like a human, manually added decision rule. In practice, Y may not be a linear function of U. Okay, but just to simplify it, you want to add this linear decision rule. Okay, and once you have linear decision rule, you can really lump this multistage multi-level optimization problem, convert them into a single level. So the key point here is with this linear decision rule, we become less adaptive because we have to deal with this extra constraint for decisions, although it could be computationally inexpensive. But the key point I want to argue here is try not to use this kind of affine decision rule if you can. Why? Because sometimes it could really lead to some observed outputs, observed decision as results. So here's one particular example I always want to show to the audience. Let's say we have an adaptive robust optimization model for a very simple facility location problem, okay? And assuming we just have these 2 facilities and 3 customers. So this is a huge problem. 2 facilities, 3 customers. Essentially you have 2 integer variables and 6 continuous variables. And if you do this uncertainty set at least. The key point here is looking at this table here, okay? If you use the affine decision rule or linear decision rule, the solution is giving you 0. So what 0 means is that, okay, don't open anything, okay? You are going to lose money, so better not to invest on this business. And why is it telling you 0? Because this affine decision rule is over-conservative, okay, and just refuse to open any of these facilities. The issue is if you really solve this problem in the general decision variable space, it ends up with a certainly nice number, about 6,600. Essentially, it's a positive value and it's profitable. Okay, so that's the key issue. If you use linear decision rule, it may work in some cases, and in some cases it won't work. And sometimes it really gives you an observed outcome. So that's what we want to adapt in this work. We don't want to stick to the classical affine decision rule, which is an approximation. Instead of doing that, we're just looking at the generalized decision rule. Okay, generalized decision rule means that it could be anything. It could be a fully adaptive solution. Okay, and a decision could be obtained from solving the inner level optimization problem. But again, it's a general function, has nothing to do with uncertainty, no direct linear connections. Okay, and of course, it's challenging to solve. I mean, you can always argue that, but being someone trained on mathematical programming, we are always good at this. So the main idea here, this is a kind of like a tailored algorithm based on the column-and-constraint generation. The key point is we try to convert a multi-level optimization problem to a single level one, and essentially become a semi-infinite program because we will have many constraints in this case. And the semi-infinite problem is difficult to solve, so we follow using a projection-based reformulation and decomposition algorithm. So you can decompose the problem into some master problems and some sub-problems and solve them iteratively. So the key point here, key idea is to really kind of explore the extreme points in the polyhedron of inner level problems. So in the end, we will have a set of sub-problems. Okay, each sub-problem corresponds to one component for the corresponding uncertainty set. And the convergence is guaranteed for the finite iterations. So it's the same as all the deterministic global optimization algorithm. This is the procedure code of the algorithm and the illustration of the algorithm. I won't get into too much details because it's not really the focus of this presentation. But essentially what you can see is similar to what you see in typical bender decomposition. You get a master problem, you solve it, you get a first stage decision, pass it on to the sub-problems, you solve them, you get some cuts, add into the master problem, and iteratively solving both stages until you reach the convergence. Okay. So that's probably the end of the theory for now. Again, let me show you some examples and with some applications. So we're still looking at the same data set we saw earlier, okay, the same uncertainty data set with U1 and U2 in this range, most data in the center and some outliers on both sides. Now we put into some specific values and a specific problem. So in this case, you have 2 first stage decisions, x1, x2, 2 second stage decisions, y1 and y2, okay? And the 2 uncertain parameters are u1 and u2. And they were kind of over here, they will be captured from the data, and we construct uncertainty set from the data. Okay, and you saw it already from data-driven uncertainty that we presented a few minutes ago. So here we try to solve this problem with 3 approaches that we mentioned earlier. The very classical box uncertainty set. Again, this problem is always an adaptive robust optimization problem. Okay, it's a 3-level mini max many problem. So you can still solve it with a box uncertainty set. You can solve it with a budget uncertainty set, and then solve it with a data-driven uncertainty set. Okay. So the objective function is to minimize the objective. So the smaller one, the better. The smaller objective value, the better. So what you can see here is the box uncertainty set tends to give you a relatively high value. The budget one is better, but the data-driven one is definitely much better. Okay. And the main reason is again based on this data-driven uncertainty set. What you can see is the box one is highly conservative, hedging against all the uncertainty in the entire space. Budget one is a little bit better. Okay, hedging against uncertainty in this area. But the data-driven one is really the best, okay? Hedging against uncertainty in the right data space, in the necessary one. There is some overlap, but that's okay, because you are talking about a union of multiple sets, so overlap is never going to be an issue here. Another example, okay, still looking at the same problem, but just changing the data. That's what data-driven is all about. Change the data and see how it looks like. So in this case, you can see the data is somehow more like just Gaussian process, Gaussian distribution, and quite correlated, because you can see U1 increase and U2 decrease. Okay, somehow correlated in certain ways. So you can still solve it in the three approaches. We can consider uncertainty from these data parameters, and then solving it with three approaches. Again, we are minimizing the objective. So the box one give you the highest one, budget one give you a better one, and data-driven one give you the best, which is not surprising. The corresponding uncertainty set will be given over here. Again, the box one is the highly conservative, only deal with upper and lower bounds. The budget one and the data-driven one, or in this particular case, these examples here, we adjust the parameters such that they cover the same amount of uncertainty data. Okay, so what you can see here is the data-driven one has a kind of wider shape, but really kind of develop a structure based on the data. And the budget one has a much bigger area, okay, or some data over here. So the data over here will be the same as the data in both sides. So they have the same data coverage. And still they end up with different decisions. And essentially you can see the objective value, for a data-driven case is better. So there's some sort of sensitivity analysis. All we can do is also try to adjust the parameters of the budget set and also the data-driven set to figure out, to cover the same amount of uncertainty data or be the corresponding objective value. Okay, so the figure here really shows we cover from 0%, essentially we don't cover any uncertainty data, it's a deterministic case. Okay, so in a deterministic case, essentially it's end up with the same solution because it's deterministic. So cover from 0% to 100%. Okay, so what you can see here is the yellow line is essentially the objective value for the budget set on the ARO, robust optimization based on budget set, and the blue line is the objective value for the data-driven adaptive robust optimization we proposed. In all these cases, the data-driven one always give you the better, or I would say less conservative solutions that hedge against the real uncertainty. Okay, and in particular, you may be interested in these two extreme points, just covering 100% of uncertain data. So what you can see here is the right-hand side is the uncertainty set. Okay, the budget set, when you try to cover 100% uncertain data, the budget set will become identical as the box set for this particular data set. Okay. Because data is somehow like reverse triangle. So budget set, if you want to cover 100%, it will be really this kind of epic area. While a data-driven set will end up with a very nice polyhedron structure. And again, in this case, it's only one component because you clearly see the data is pretty much neat, or pretty much compact. Okay, but by looking at the area, you can definitely understand why the objective value will be different in these two solutions. All right. So this is the numerical. These are the numerical examples. Now let's get into some applications. All these methods and frameworks can sort of be applied to a variety of topics and application domains. Being a PSE community, I just want to show you some kind of applications to planning and scheduling problems. So first application is scheduling problem. This was originally coming up from our earlier collaboration with Dow Chemical. So essentially, try looking at these 4 raw materials, 6 intermediate products, and 4 products through a number of equipment units and a few tasks and steps. I try to maximize the profit and subject to a few constraints. So major uncertain parameters coming from the demand of the products and from the processing times. Okay, and the demand of products will be correlated and sometimes highly correlated because some products are quite similar. Processing time will involve some outliers, and these outliers could really prolong the processing time if you use a very conservative approach. So this is the result, okay, which again, we're trying to compare the 3 approaches, the data-driven one, with the budget one, and with the box uncertainty set one. So with the box uncertainty set, as we mentioned earlier, there were some outliers about the batch processing time. So it turns out that we would end up with a very long processing time, which is not really realistic. And that's how it works, because once you get outliers, box set tends to be overly conservative. Okay, budget set in this case, it's a little bit better, at least for R2, you can see it's shorter, and some other tasks is better. But overall, if you're looking at a profit, okay, they're pretty much identical. Okay, not that much better. But with data-driven set, you end up with a more kind of normal or reasonable Gantt chart, where they really capture what's going on and still hedge against uncertainty. And in fact, you can see if you're looking at the profit here, The classical approach really give you about $34,000, and the data-driven one give you about $46,000 or $47,000. So that's really about 30% increase in terms of profit. So data-driven approach really help you to reduce the conservativeness and also improve the solution quality. Another application is on process network planning, and this is another classical example you get to see a lot of design planning problems in process systems community. So this is essentially a process network with 38 processes and 28 chemicals. Okay, so you get 10 materials, 10 chemicals materials, 16 chemicals could be used as products. So you have 26 dimensions in this case. And of course, we get a bunch of thousands of data points for supply and demand uncertainty. And the objective is to maximize the net present value subject to some constraints on capacity expansion, investment, mass balance, and demand, supply, and so on. Okay. So again, we can solve this problem using a static robust optimization with box uncertainty, using a budget uncertainty with adaptive robust optimization, and using the data-driven adaptive robust optimization we propose here. We are maximizing the net present value for the mounting per unit, so the high objective value means better. So what you can see here is the box set giving you a relatively conservative solution. Budget one give you something better, something higher, and the data-driven will really give you much better one. Okay. And this is, of course, you can argue based on the selection of specific parameters on uncertainty data coverage. So you also end up with the heat map here. And what you can see here is what we get over here, A57 corresponds to this particular value. But even looking at the worst case, it's still better than the budget set. Okay, so no matter how conservative it is, how much we adjust it, we always perform better than the classical robust optimization approach or conventional robust optimization approach. So this is a decision you get to see as a comparison of process network design planning outcomes. It looks a bit messy or a little bit complicated, but essentially what you can see here at the bottom is a legend. So we are telling each box upper level gives you the process, and the number at the bottom gives you the capacity. Okay, so for example here, this P12 was not selected in the solution for static robust optimization, but P12 was selected in the data-driven adaptive robust optimization case with a capacity of 14,000 times or something like that per year. And so then there are some difference in terms of solution. Like in this case, this guy was selected and this guy was not, and this guy was selected here, this guy was not. Okay, so the decisions tends to be quite different, and that's what we argue. Robust optimal decisions must be coming from a data-driven approach to make it true optimal. So one last piece is on computational efficiency. We talk about solution algorithm, and we talk about this column-and-constraint generation method, essentially for solving the master problem and solving the sub-problems. You end up with the upper bounds and the lower bounds. Okay, so as the iteration goes on, upper bound decrease and the lower bound increase, so that we could close the gap. Okay, eventually close the gap to 0%. And this problem could be solved still relatively fast, in about 6 minutes. And I will not stress that the problem cannot be solved by any off-the-shelf optimization solvers, because none of existing off-the-shelf optimization solver could really handle these multi-level optimization problems. Okay, so computational-wise, this is quite acceptable and reasonable. So this is a summary about what we talked about so far. For this data-driven adaptive nested robust optimization case. If you're interested in learning more details, the paper was published a few months ago, I would say. Over here, this is a complete reference on data-driven adaptive nested robust optimization, general modeling framework, and efficient computation algorithm for decision-making under uncertainty. Okay. So in the next few minutes, let me quickly just going through another extension that we think about is a unified framework for this data-driven decision-making under uncertainty. So everything we talk about is essentially we have a holistic framework to perfectly combine machine learning and mathematical programming. And of course, passing through information in the meantime. We get data in, we get decision out. Okay, and of course, the machine learning here could be directed process mixture model, could be kernel density estimation, or any machine learning techniques. Mathematical programming approach could be stochastic programming, could be robust optimization, among others. But what we have been mentioned earlier, essentially we talk about data, or you're only dealing with one kind of data. Okay, we don't really differentiate them. We don't assume there's any label. But essentially, you can see in the existing computer science literature, in machine literature, they're really dealing with a lot of effort, spending a lot of effort to deal with the labeled data, or multi-class data. Okay, and why these are so important, you can see, because there are a lot of practical applications relevant to the uncertainty data with labels. For example, okay, in the energy sector, we talk about solar panels. You can really collect data in terms of solar power generation, all right, real-time data or visual data. And in some cases, these data are generated along with some kind of label. And this label could be weather conditions. It's sunny, it's cloudy, it's raining, or it's snowing, or maybe it's a sandstorm or some kind of conditions. Okay. So this label information turns out to be very useful and very valuable. But in most cases, if you use a previous approach, we just did not fully capture the value of this label information. In the process industry, there's a very classical process control paper, okay, looking at the process data generated from this Tennessee Eastman process with 6 operating modes. And each mode has its own mass ratio and production rates, okay? So the different modes, I mean, any data created with different mode and now with the corresponding data that we can leverage and we can utilize. So going back to decision making under uncertainty, when we talk about sequential decision making under uncertainty, which is better because you can really capture the decision making process. Some decision made before uncertainty is realized, and some decision made after uncertainty is realized. So in the two-stage stochastic programming approach, you can really capture this kind of sequential decision making process as well. Same, and the key major, key component or key properties is that with the two-stage stochastic programming, you can make full use of the probability information. And of course, this is based on assumption that you could get a very accurate probability distribution. If the probability distribution is not accurate, it becomes a distribution robust optimization case. Your shared distribution is uncertain. And in some cases, you can really see the computation could be very challenging because if you have a large data space, okay, you get thousands or millions or billions of data points, and if you try to use one scenario for each particular data point, the computation could be very challenging. For robust optimization, on the other hand, computation could be relatively efficient compared to stochastic programming, and does not really require the exact probability distribution. But sometimes people will say you could end up with some conservative solutions because they're really hedging against the entire parameter space. So the research questions can leverage the strengths of both. And of course, the answer is always yes, we can, all right? Yes, we can. So what we do here is something called data-driven stochastic robust optimization. Okay, this is a unified framework to capturing both cases. So you begin with the label multi-class uncertainty data. Okay, this data will be labeled with multiple class and you will be correlated or symmetric in any other kind of matrix structure. We use machine learning techniques with the maximum likelihood estimation and differential process mixture model to generate a group of deeply mixture models based on uncertainty sets and probabilities. Okay, then this uncertainty information will be further combined and solved in a nested stochastic robust optimization problem. So you get outer label for stochastic programming and inner label for robust optimization. Okay, so from machine learning perspective, this will be deeply mixture model which we mentioned earlier. We can use MLE to come up with a parameter, come up with a probability for each particular data class, and then use the DP to come up with these unions of multiple basic sets. Okay, so I'll skip this quickly because we are approaching the room, approaching the end of the presentation now. So very briefly, the data structure involves something like this. We have the upper level of expectation, looking at stochastic programming, and then the inner level will be robust optimization. Okay, we still have the data-driven uncertainty set. So conceptually or theoretically, you can consider this data-driven stochastic robust optimization as a generalization of the previous approach we talked about. Okay, or on the other hand, you can say the previous approach is really a special case when there's only one data class in this particular data-driven stochastic robust optimization. So there's a scope of application, only one data class, or you get unlabeled data. So very quickly, an example here, a numerical example with three uncertain parameters, U1, U2, and U3. Okay, so these uncertain parameters will be generated from a data set. We could get here. Okay, this is uncertain distribution with 1,000 uncertain data points and 4 different data classes. Okay, so these 4 data classes, some of them are here, some are here, some groups here, some groups are here, and they could be correlated, asymmetric, and multimode. All right. So we still solve this problem using different approaches. Two-stage stochastic programming. Okay, and the idea is very simple. You use one data point as one scenario, so you end up with 1,000 scenarios in this case. DDANRO is the one we talked about earlier. We just forget about, discard all this label information, treat all the data in a homogeneous way, and data-driven stochastic robust optimization is something we're talking about here. Okay, so what you can see here is with stochastic robust optimization, we can end up with multiple groups, multiple union sets. Okay, and this data class will still have multiple nice polyhedrons to cover them in a very compact way. Okay, and by looking into the computational time here, okay, the two-stage stochastic tends to be more computationally intensive than the stochastic robust optimization. And the issue here is we only get 1,000 data points. Think about if you get 1 million data points or 1 billion data points, these guys will be still pretty much the same, but this time will really increase exponentially because of the structure of stochastic programming. Okay. So we also do some further validation to simulate deterministic solution value, which I could really skip it quickly, but essentially looking into these cases and see this proposed method turns out to be much better for classical stochastic programming and to the previous case in terms of deterministic objective value here. So all the details about this stochastic optimization was ready. We posted online archive. If you know about archive, it was from Cornell, one of the Cornell library product. If you're interested, you can look into this paper on data-driven stochastic robust optimization, a general computational framework and algorithm for optimization under uncertainty in the big data era. So the last few minutes, let me quickly go through some other things we have done in this field. One direction is looking into data-driven robust optimization with the kernel learning. Kernel learning in this particular case is a support vector clustering. Okay, so here we use the support vector clustering to generate this kind of piecewise linear uncertainty set. It turns out to be very nice, although it's a QP. Essentially, you can still come up with a very tractable, robust formulation, and it could be similarly applied to this process network planning or scheduling problems. So this paper was published by postdoc Dr. Chao Shang, and the paper was data-driven robust optimization based on kernel learning, and published in Computer and Chemical Engineering recently. Another direction, of course, we have extended this approach to the multi-stage adaptive robust optimization, because we talk about two-stage, but now we can really look into multiple stage. So the decision will be made here now, and uncertainty realized in stage 1, and then we have recourse action in stage 1, and then we make a decision again, and we get uncertainty again, and we recourse again. Okay, keep moving forward until stage T. So this becomes multi-stage robust optimization from a data-driven perspective. In this case, we use a kernel density estimation and combine with robust statistics. Okay, so it really goes beyond the classical statistics. For example, with the box uncertainty set, we know this is pretty bad. Okay, but even with KDE, you would think KDE, kernel density estimation, is a very well-known machine learning or statistical method. It still gives you something relatively conservative. But with the robust KDE, robust kernel density estimation, we do really get a very compact solution, a very compact uncertainty space. And of course, this approach can also deal with the correlated uncertainty and could be applied to batch scheduling and process planning. So this paper is also published called a data-driven multi-stage adaptive robust framework for planning and scheduling under uncertainty. Okay. So let me draw a quick conclusion in the last minute. I will say here is very much a merge or marriage of machine learning and robust optimization. And on one hand, it leads to this very nice integrated decision-making framework, okay, that has a data-driven component, also model-based systems component, and put them together in the comprehensive COCOM, or in the particular core. And here we leverage the power of big data analytics for optimization under uncertainty. But more importantly, the merger of machine learning, meeting of machine learning and robust optimization really bring the theory and the methods in both fields to the next level. And this leads to data-driven scientific discovery of a new and very powerful robust optimization paradigms. There are new ideas to build these very flexible and very powerful uncertainty sets that were really previously intractable. And this modeling algorithm framework for big data-driven optimization is really going to be helpful in many applications, as you can see in planning, scheduling, among others. And also intended to contribute to the new theory and algorithms, mathematical programming, and also empower machine learning to go from data to information and follow to optimal decisions. So thank you for your attention, and I think we are somehow quite on time. I'm not sure if you have any time for questions, but I'd be happy to answer any question here or offline. Thank you.
Okay, well, thank you, Professor Yu. We'll have just time for maybe 1 or 2 questions, and I put in the chat window if you'd like to, just a note there, if you'd like to ask a question there, or you can unmute your microphone. So we'll open it up for questions at this point. We'll just have time for 1 or 2. Okay, so I had a couple questions. I'll just ask one. I was just wondering about you're designing this solver because there's no essentially off-the-shelf solvers that can handle this type of optimization problem that you formulated. Are there any? What do you think about some of the architectures for optimization? It sounds like with stochastic programming, things like GPUs might be beneficial. What are some of your thoughts about architectures that might be able to solve this type of problem more efficiently?
Absolutely. Thank you. This is a very good question. So essentially, this is a decomposition-based algorithm, right? It's not the same as the vendors, but it's somehow similar. You still have a master problem. You have a few sub-problems. So if you could parallelize the subproblems, for each subproblem solving each kind of distributed systems, then essentially this computation could be highly speed up, and really depending on number of components and number of subproblems we have. So yeah, it's possible because I know there are some solvers for solving stochastic programming problems at large scale using some sort of decomposition algorithms. So probably in the long run there could be some kind of solvers that could solve these kind of problems, multi-level optimization problems. But essentially, the key point is this is a general class of multi-level optimization, minimax, min, or max, minimax, and so on. And that tends to have a lot of increasing applications, not only in robust optimization, but also in other domains. Like game theory, even in stochastic programming, it tends to also see something like this more and more often. And I'm sure in the long run, there could be some solvers that could handle this. But at least for now, we do have a very nice algorithm that could be the foundation of the solvers in the future.
Great. Okay. So any other questions from the audience? So let me ask maybe just one more, since we have another one coming in. But we have these polyhedral sets that you define. I'm thinking about the multi-dimensional case where you might have some covariance or other information that helps you define that uncertainty region. And I imagine in high dimensions, it could be much more difficult to kind of get your mind around, where you define those points or define those regions. I was just wondering if you have any thoughts on that.
So, well, I mean, machine learning is really dealing with high dimension case, right? So, for human, we really deal with 2-dimensional, 3-dimension case. Once we could visualize them, you could probably know what would be the best shape to capture this information. But for high-dimension case, there are systematical ways to use them, and one of them would be this one. We talk about this directional process mixture model, and the other one could be things like robust kernel density estimation and so on. They could really deal with high-dimension case. You don't need to see them; you just need to use this particular algorithm to follow what's going on to extract useful information from statistical principles.
Okay, great. Okay, well, thank you very much. It's been a pleasure to have you present today. And what we'll do is we'll end the recording and then post this online. Again, if you'd like to share it with, for those who joined, if you'd like to share it with colleagues. And we'll have our next webinar coming up in a couple weeks. Thank you, Fengqi, for the very informative and thought-provoking discussion. It's not often that we see a presentation about robust optimization and uncertainty and how those with machine learning and how those all meet together. So thank you for the informative discussion and presentation.